Take a look at this macro footage. In slow motion, a thick, dark sludge is rapidly creeping over and suffocating a clean, porous surface. This is what catastrophic fouling looks like at a microscopic level. It can choke a multi-million-dollar water treatment system in a matter of weeks. Industrial reverse osmosis membranes are engineered with a multi-year lifespan, yet plant managers routinely watch these heavy-duty assets fail within a few months of installation. When you call the vendor to investigate the failure, you almost always get the exact same generic explanation. They will blame it entirely on scaling. This diagnostic report illustrates the problem. You see a sharply dropping financial graph masked by a massive red stamp reading scaling. Accepting the superficial one-word diagnosis is a critical operational error. It gives the illusion of an answer while completely masking the deeper systemic issues occurring inside your plant. The true consequence of this misdiagnosis hits the bottom line directly. You end up authorizing capital expenditures for unnecessary, repeated membrane replacement cycles. To stop the financial loss, we have to move past reactive symptom treatment. Plant stability requires running a structural, proactive root cause analysis. This diagram outlines a comprehensive RCA framework. Instead of looking for a single culprit, isolating failure modes requires investigating across 7 distinct vectors, organized into chemical, physical, and operational categories. Accepting a generic one-word diagnosis for a complex fluid system ensures a continuous loss of capital. Achieving plant stability requires mastering this 7-vector diagnostic model. We begin with the chemical and biological category. These are unseen, microscopic attacks that degrade the membrane's structural integrity long before you notice any physical pressure drops on your gauges. Cause number 1 is true scaling. This extends far beyond generic calcium buildup. It represents a failure in precise, continuous chemical monitoring. Severe scaling takes hold when the Langolier Saturation Index, or LSI, is ignored, or when the plant utilizes a completely incompatible antiscalant chemistry for the specific feed water. The operational mandate to prevent this is strict. You must optimize the LSI to sit between negative 0.2 and positive 0.2. Furthermore, you must enforce the use of flow-paced dosing pumps, calibrated strictly by empirical jar tests. Cause number 2 is biofouling. Rather than a mineral deposit, this is an active biological invasion triggered by specific environmental oversights. When inadequate pretreatment meets feed water temperatures exceeding 35 degrees Celsius, your system becomes an incubation environment for rapid biofilm growth. Eliminating biofouling requires 3 operational mandates. Maintain a feed silt density index strictly below 3, implement UV or chloramine biocides upstream, and utilize 0.1% sodium hydroxide during your CIP routine. Skipping to the final chemical threat, cause number 4 is oxidation attack. The thin film composite layer of the membrane is exceptionally vulnerable to chemical oxidants. Watch this dense polymer lattice being rapidly shattered by incoming aggressive chlorine particles. Free chlorine exceeding 0.1 ppm causes irreversible polymer oxidation. To prevent this, mandate the installation of ORP meters tied to auto-shutdown interlocks. As a secondary requirement, sodium metabisulfite dosing pumps must be strictly calibrated on a weekly schedule. Chemical and biological negligence silently hollows out the membrane structure, destroying the utility of the asset long before macro-level alarms trigger. Moving away from microscopic chemistry, we must look at macroscopic kinetic forces and physical blockages. Cause number 3 is colloidal or particulate fouling. The mechanism here is straightforward. When upstream 5-micron cartridge filters are damaged or improperly seated, raw physical particulate entirely bypasses your pretreatment phase. The mandate is discipline. Enforce rigid, time-based filter replacement schedules rather than waiting for a failure, and conduct monthly audits of your pretreatment efficiency. Cause number 5 is mechanical damage, specifically a severe structural deformation known as telescoping. Turbulent fluid violently slamming against a solid barrier. This is the kinetic energy of a sudden pressure surge moving unmitigated through a contained system. Sudden pressure changes, often caused by improper startup or shutdown sequencing, physically push the tightly wound membrane layers out of alignment, sliding them outward like an extending telescope. You correct this by integrating slow open and slow close control valves, and by rigorously auditing your anti-telescoping devices, or ATDs, during every cleaning cycle. Even if your water chemistry is perfectly balanced, kinetic violence resulting from poor fluid handling protocols will physically shred the system's architecture. The final category of failure stems from human-introduced errors in system design and cleaning protocols. Cause number 6 is concentration polarization. This is a direct consequence of operational overreach. Pushing recovery rates beyond 75 to 80% without increasing cross-flow velocity builds a hyper-concentrated particle layer on the membrane. System recovery must be continually recalculated based on feed water total dissolved solids, ensuring cross-flow velocity clears this buildup. Cause number 7 is destructive clean-in-place protocols. Extreme pH levels or excessive temperatures during routine cleaning doesn't maintain the membrane, it actively accelerates its degradation. Strict CIP mandates must be enforced. Lock your pH between 11 and 12 for organics, use pH 2 to 3 for scaling, and enforce an absolute temperature ceiling of 45 degrees Celsius. And the final mandatory step, always execute a permeate flush post-cleaning to ensure residual harsh chemicals are removed from the housing. Operational ambition for high recovery rates, combined with aggressive maintenance routines, can paradoxically be the exact forces that degrade the membrane. Now that we've completed a retroactive autopsy of the 7 failure modes, we must shift to a system of proactive daily defense. True plant optimization relies on taking this root cause analysis framework and tying it to strict continuous KPI interlocks. Look at this SCADA dashboard displaying 5 critical metrics. The first is normalized permeate flow. A drop greater than 10% is the earliest indicator of systemic fouling. You must act immediately when you see this dip. The second metric is salt rejection. A sharp drop here confirms that physical, structural damage to the membrane has already occurred. The third metric is differential pressure. A rise greater than 15% confirms severe, flow-restricting fouling is blocking the feed channels. Metric 4 is feed SDI. It must strictly remain below 3 at all times to guarantee your pretreatment integrity. The fifth and final metric is ORP. Target this strictly below 200 millivolts post-SMBS dosing to prevent intoxication. Connecting these daily digital readouts to the PLOD's operating budget allows for precise financial planning. These gauges represent the measurable difference between controlled operation and the cost of unplanned downtime. When you enforce these KPIs, you shift your plant's operational posture from reactive firefighting to predictable, scheduled maintenance. By discarding the scaling myth and enforcing these 7 vectors and 5 KPIs, you can extend the life of your membranes by 3 to 5 cycles, reducing recurring maintenance costs and stabilizing the plant's production capacity.